How'd the video watching go? Good. Did it make sense what I was talking about? Well, we're doing examples today too, but did it make sense what was going on?
Yeah, so I guess that was what we did that in Calc 3.
Yeah, you would have done the same thing in Calc 3 if you were doing it with like the cross product idea.
Yeah, but we weren't ever worried about like taking a certain row range.
Right.
We always did the top row.
Right, you always use the top row because of the IJK piece for the cross product.
Do you have to use the top row for the?
Nope, you can use any. You can use any row that you want as long as you keep the numbers and the vectors in the right spots. You can actually use any row or column as long as you keep the vectors in the right spots. So yeah, same idea. Basically, all of this stuff that we're doing ends up with the same answer. Obviously, otherwise it'd be a really, really bad way to define it. But it all amounts to trying to keep track of products and how the products go. So let's do another example with row reduction, and then we'll do one with cofactor expansion like we mentioned last time. So let's say it all depends on the complexity of the matrix and what you're actually trying to row reduce in this case, because a little better than it was. I had one of those things when I worked at the University of Evansville. They remodeled their engineering and science building and added on, not unlike what they did with the Commons, with the adding on. But when they installed the screens for the projectors, instead of actually, you can see how those chains are going up through the hanging ceiling and actually attached to something, they just attached them to little slats in the hanging ceiling. So I pulled it out one day and it fell down and hit me in the head. So a little nervous with the whole projector thing. All right. So the method that you use to compute the determinant depends a lot on how the matrix is set up to begin with. And that was kind of the point with the video as well. If you've got a matrix that has lots of zeros in it, using a cofactor expansion is helpful because you're going to be doing lots of products of 0 times something, which just kills the whole thing. And you have smaller, you can break it down to smaller determinants and not have to do as many computations. However, if you've got matrices that don't have lots of zeros and ones entries, then you're going to have to do a lot of products to be able to do it. And then row reduction is more efficient to be able to evaluate the determinant. Because again, when we do row reduction, really we only have to get it triangular. We don't have to do full-blown Gauss-Jordan, get it down to the identity row reduction. We just need to get a triangular matrix and then multiply down the diagonal to get the determinant. We talked about that last time, right? So, pardon me. Let's just do another example where we use row reduction. So let's say that we have the matrix, let's say 3, 1, 0, negative 2, 4, 3, 5, 4, negative 2. And let's say we want to do row reduction on this. So if we're going to do row reduction again, we want to get a 1 in the upper left-hand corner. There's a couple of ways we can do that. So, and when you're doing things with the determinant, sometimes it's helpful to be a little more clever, because we know that if we do the row operation where we do a multiple of one row and add it to another row and replace the second row, it doesn't change the determinant at all. If we can use that one to help us row reduce, that'll eliminate having to worry about how the determinant changed from step to step. So looking at this matrix, can I get a 1 in the upper left-hand corner without having to multiply just a row, dividing row 1 by 3, say? Is there a way to get a 1 up there without having to divide row 1 by 3?
Yes.
Yeah, what can I do?
Add row 2.
Good. So we can take the original matrix and we can take row 2 plus row 1 and replace row 1. So it doesn't change row 3, 2 or 3. I really should be writing vertical bars here because I'm trying to do the determinant. So let me change those to vertical bars. When we add, I just said, let me change it to vertical bars and immediately wrote brackets again. When we add, what do we get? We get 1, 5, 3. And again, since we did this operation, these determinants are actually equal to each other, right? We didn't change the determinant at all because we did an operation, an elementary row operation of this type. So again, our goal here is just to get to triangular. Again, we don't need to worry about reduced row echelon form or anything along those lines. We just need to get to triangular. But again, the reason why we got the 1 in the upper left-hand corner is to help us get zeros below it. So we can do -2 times row 1 added to row 2, replace row 2, whoops, +2, and -5 row 1 added to row 3, replace row 3. That'll take care of the zeros below, right? So let's see here. This becomes 0. What do we get? 14 and 9. If I did my arithmetic right. And the other one we get 0 and let's see, -21 and -17. Again, if I did my arithmetic correctly. As far as good? All right. So, again, how did that change the determinant? It did not. Good. They're the same, right? Didn't do anything at all. All right. So, again, our goal here is to get to triangular. So, I don't even really have to worry about getting a 1 in where we typically get 1s when we do row reduction, right? If I can get to triangular, then I can just multiply down the diagonal, and it gives me the determinant of the matrix. Right? So I look at these two numbers. If I multiply this one by 3/2 and add, it'll make that a 0 below it, won't it? And then again, it won't change the determinant at all. So why don't I just do that to save me a little bit of work? Do -3/2 row 2, add to row 3, replace row 3. So 1 stays the same. Yeah, good grief. I don't know why I can't keep my signs straight today. Thank you. 0, 0. And then we get, pardon me, 27/2, and then -34/2. So that's -7/2. Again, if I did my arithmetic correctly. No, I just realized I forgot to write down your assignment. I'll do that here in a minute. If I don't do it while I'm thinking about it, I'll forget by the end of class. And then they'll get an email from me. All right, so again, now we didn't change the determinant at all. So we've gone through this entire process using the same type of elementary row operation, and it didn't change the determinant at all, right? So now, though, we've got triangular, so when we do the determinant, all we need to do is multiply down the diagonal to give us what the determinant is. I copied the problem out of the book and forgot a negative sign out of the book. That's why I didn't get the same answer as what the book was getting, but I changed the number. We should get -49. Again, nice thing is you can check your answers on the calculator because your calculator will do determinants too. That's okay?
Calculator do inverses?
Yep. As a matter of fact, if you type in the matrix, if you just use the -1 button, it'll do it. So if you've got your matrix already typed in, So when you go and grab the matrix by its name, it looks like with brackets around it, right? If you just use your little -1 key, it'll take the inverse. So you can do it that way. You can check your answers that way too. Yeah. That's okay? So using this process of row reduction, we can get the matrix, the determinant of the matrix as well. But again, like I mentioned, sometimes when you do row reduction, or sorry, when you want to do determinants, sometimes it's a little bit more efficient if you've got lots of zeros and lots of ones. So I'll do an example here with cofactors to see how that works. Again, that was just like the video, but let me write your assignment down before I forget. So 9 and 12 on page 95. And then for practice, I guess it's actually page 94 where it starts. And then for practice, 3, 4, 5, 10, 11, 22, 25. And then 9 and 13 on page 101. And for practice, 2, 3, 5, 7, 8, 11. Again, the ones that I'm writing over here on the writer for practice. And then 5, 13, 16, page 109, 3, 4, 6, 7, 8, 10, 12, 15, 18. This will be due on next Wednesday, which is what, the 26th?
On the first row of practice, is that 3, 4, and 5, or is that 3, 4, and 5?
There we go. All right. So let's see if we can do one of these with cofactors. So let's just make one up here. So let's say I want the determinant of, let's say we had 1, 7, 8, 0, and 15, and then let's say we had 0, 6, -2, 0, 9, and then let's say we have 1, 0, 3, -1, 8, and let's say we have 0, 2, 5, 0, 7, and finally maybe a 0, -3, 4. I'm just making it up as I go along here. All right. All right. So again, the whole idea, actually any of these methods that we're doing with taking determinants is all about trying to keep track of products out of the matrix. So the actual technical definition of determinant is you make all possible products that you can out of the matrix by choosing elements from each row, but you don't repeat columns. So one of those products, for example, could be 1, 6, 3, 0, 2. That gets an element from each row and I didn't repeat any column, right? But you could also do 7, 0, 3, 0, 2. And keep playing around those ways. Now, think about it. I got 5 choices for the first row, but once I make a choice out of the first row, I can't repeat a column, so I only get 4 choices for the second. And then I can't repeat the column from 1 or 2, so then I get 3 choices for the third, right? For making these products, and so on down the line. So for an n by n matrix, there's n factorial products you have to compute. That's a lot to keep track of. So what you're doing this matrix, if you were actually doing it by the definition of, the actual technical definition of determinant of a matrix, you'd have to do 120 products. That's a lot of products to try to keep track of, make sure you chose them all correctly, right? So doing these different methods of calculating the determinant, either by doing row reduction or by doing this expansion by cofactors, expansion by minors idea, both of these are just ways to help you keep track of all those products. Okay? That's all they are. It's just different methods for trying to keep track of all of these products. So the other thing you have to pay attention to as well with these ideas is the idea of what type of permutation do we have? Do we have what's referred to as an even permutation or an odd permutation? And that tells you whether or not the sign is positive or negative on it for the product. So all we're doing is trying to keep track of these things instead of trying to go through all of that mess to do the actual definition of the determinant. All right. So when we do expansion by cofact, and this is why when we do this expansion, like I mentioned in the video, you eliminate the row and the column that you're talking about when you pull things out. By eliminating the row and the column, you're making the choice of, I picked this row and I don't want to repeat this column. And so that's how it keeps track of all the different products you need to do. All right, so one of the things we notice in this particular matrix is this column has lots of zeros in it, right? So when we expand along this column, the only one that matters is this one, right? Because the rest of them we're going to do 0 times the associated, what we refer to as the associated determinant of the minor. Whenever you expand along a row, when you expand along a row or a column, the end of it, the matrix that's left after you eliminate the row and the column, the matrix is referred to as the minor associated with that entry. So this is the 3-4 entry. So the 3-4 minor says take out row 3 and column 4, and right now it's left. Okay. All right, but again, the only thing we need to worry about is this -1 that's right here. The rest of them don't matter. So there's 2 things I have to worry about. Number 1 is the minor, the determinant of the matrix that's left, after I eliminate that row and column. But I also have to worry about whether or not this is a positive or a negative out in front. And that was that idea of the sign board that I was talking about in the video. Okay? So remember, for the sign board, it's easy to make. It always starts with a plus sign in the upper left-hand corner, and you you alternate as you go across columns. Go across the rows or down the columns. And like I mentioned in the video, you should always see plus signs going down your diagonal. Okay? So where this -1 corresponds to right here, doesn't it? So that should have a negative sign out in front. Just the extra thing we have to keep track of. Again, this is keeping track of whether or not the permutation that we're using, the selection of entries from each of the rows and columns, results in an even permutation, which would be positive, or an odd permutation, which would be negative. Okay. All right, so after we eliminate row 3 and column 4, we're left with what? 1, 7, 8, 15, 0, 6, -2, 9. We eliminate row 3, 0, 2, 5, 7, and 0, -3, 4, 2. Everybody okay with that part? Where I got that matrix from? Yeah, Megan.
You're taking out one of the rows because it's out in the front?
I'm taking out the row that's associated with that entry because it's out in the front. Yeah. I didn't write out the other ones, but that would be what we would have. All right. So far, so good? All right, so now I've reduced this 5 by 5 matrix to a 4 by 4. But notice that in this 4 by 4, I've got another good column to expand along, don't I? I've got this 1 here, and the rest of these are zeros. So I'll color that in red again just to be consistent. So let's expand along that row. Try that again. Expand along that column. There's only going to be one non-zero entry in that column, but I also need to make sure that I keep track of these numbers in front too. Don't lose them on the way down. However, in this case, I got a negative 1. So if I lost it, it wouldn't be a big deal because that's just going to turn out to be 1, right? Okay. So this is just going to equal, well, this is a negative 1 is just a 1. We will have 1. Is this a positive 1 or a negative 1 going to be up here? Positive, right? The one in the upper left-hand corner is positive, so it'll be a positive 1. And then what matrix are we left with that we're trying to take the determinant of after we eliminate the row and the column that 1 is in?
6, negative 2, 9, 2, 5, 7, negative 3, 4.
Good. Now we have 1 times that, and that's going to go away as well. So we have now reduced our matrix, our 5 by 5 matrix, to a 3 by 3. You take the determinant of. Now, looking at this one, if we're going to continue with expansion by minors, we don't have a lot of benefit for picking one row or one column over another one, right? So, literally does not matter which one we do. Just to shake things up a little bit, let me expand along the third row, just because. Okay. So our coefficients, after we expand along, will be negative 3. It'll be 4 and a 2. Is this negative 3 going to be associated with a plus sign or a minus sign from the sign board? It's a plus, right? So if this one's plus, this 4 must be minus and this 2 must be plus, right? And now we need the associated 2 by 2s, the associated 2 by 2 minors associated with each of those coefficients. All right, so what goes along with the negative 3?
Negative 2, 9, 5, 7.
Okay. Everybody see why? Eliminate the row and the column. If I take out this column and that row, I'm left with that upper right-hand piece. Oops, lost my 6. All right, what's the associated determinant here with the 4?
6, 9, 2, 7.
Okay. Everybody see that one? And then the last one's going to be
6, negative 2, 5.
good. Yeah. Thank you. All right, cool. And then once we've got it down to 2 by 2s, things get easy. For 2 by 2 matrices, we can take the determinant by taking this main diagonal, doing that product, and subtracting the off diagonal, that product. So we'll have negative 3 times, negative 2 times 7 is 14, minus 45.
Negative 14.
I even said negative 14, didn't I? Jeez. Told you, I can't keep track of negative signs today. 6 times 7, 42, minus 9 times 2, 18. 6 times 5 gives me 30, minus a minus 4. And then somebody's got a calculator to simplify that. I don't feel like doing that in my head.
Yeah, -200.
Okay. I'll trust you. Uh-oh. Uh-oh.
So when you do the cross multiply, you subtract the two, you got that.
You subtract the two, yeah. Okay, you do the product of the main diagonal and then subtract the product of the off diagonal. Positive?
Yes.
Everybody okay with the process? Now, you could have mixed methods too, by the way. We got to this point where the 3x3 didn't really have any, I mean, this part wasn't hard, right? Doing that expansion and then doing the determinants real quick. But you could have also done row reduction at this point. There wasn't any real computational advantage necessarily to do expansion by minors, doing cofactor expansion. You could have done row reduction, because one of the reasons why I thought row reduction, that might be a little bit quicker, is because notice if I add row 3 to row 2, I get a -1 in that second spot. You can get a 1 quickly in the first column. So it's, you can mix methods if you'd like. This okay? Again, one of the reasons why we use the cofactor expansion is when we have lots of zeros and ones in a matrix where we can expand along and do products simply, right? Notice that technically, and I mentioned this in the video, technically when we did this expansion here, we have 5 things that would pop out, right? But 4 of them are 0 because they get multiplied by zeros. Again, technically when we do this expansion, there's 3 more things here. But again, we do multiplication by 0, so those all go away. That's one of the reasons why we use the cofactor expansion, because they go away quickly. Yeah, Megan?
Just making sure, with this method, you can do either rows or columns.
You can do rows or columns. Yep, doesn't matter. Yeah. That was why I went ahead and just did a row in that third step. You get to pick whatever's most convenient for you for doing the products. Yeah, it literally doesn't matter which column or which row. Any other questions on that at all? Is the process okay? Okay. All right, so let's talk a little bit more about properties of determinants, because we haven't talked much about what they're used for at all. So one of the things that we're going to be interested in is that we can use the determinant as a test for invertibility. Okay? So to get to that, let's just talk about how we do the determinants of our elementary matrices. So if we have an elementary matrix, we talked about this a little bit before. If I've got an elementary matrix that's just a bunch of 1s down the diagonal until I get to a certain spot where I have a different constant, and then 1s everywhere else, and then I've got 0s everywhere else. So this is just the elementary matrix where we've taken row I in the identity matrix and multiply it by a constant. What does that do to the determinant again? What is it, or what does the determinant equal to, I should say? Just that constant, right? In particular, it's C times the determinant of I, but what's the determinant of I again? Yeah, just 1, right? So we get C. We've talked about this before, correct? Yeah. So when we take this particular, let me just refer to this elementary matrix for simplicity as E1. If I take this E1 and I multiply it by some other matrix A, well, what does this multiplication do? When we multiply by the elementary matrix, what does it do to the A matrix? What is this? When we take the elementary matrix and multiply it by the matrix over here, what does that do? What's the result? What happens with the result?
Row I and things.
Good. Row I and A is multiplied by C, right? So when I do this, all I've done is just change row I here by C, a factor of C. What does that do to the determinant of A?
Also,
It multiplies it by C, right? So this part here, the result is row I of A is multiplied by C. So this must be C times the determinant of A. Bless you. Right? But what else did we just say has a determinant of C? Well, that was E1, right? Do you agree? Okay. So-
where'd you get the determinant of E1? You just substituted C because C is what the determinant of E1 is.
Yeah, that's right. Yep. So notice in this case, what does it look like the determinant function did? It distributed over the product, right? Well, let's see if it does it again. Okay. If we do, let's say I do a row swap, instead of writing out what the matrix looks like, let's say E2 is row I and row J swapped. Okay. Then what's the determinant of E2 in that case? We talked about this last time. What happens to the determinant when you swap rows?
negative.
Yeah, so it'll be -1, right? So when I'm using the capital E, I'm referring to an elementary matrix. So what I mean, I didn't write it out explicitly in that sentence. When I write out row I and row J are swapped, I mean that you've taken the identity matrix and swapped row I and J. That make sense? Got it? All right. So, what does the effect then of multiplication have on the A then, on the determinant? Again, if I take E2 times A, what does the result give me? The row swap for A, right? And when we do a row swap, what does it do to the determinant? Makes it negative, right? So this will be the negative of the determinant of A, but we just said that the determinant of E2 was -1. And what does it look like happen with the determinant function again? It distributes over the product, right? Well, there's only one more type of elementary row operation. The complicated one, right? Constant times one row added to a second row, replace the second row. In that case, what's the determinant of E2, or E3, I mean? What does that row operation do to the determinant? Just leaves it the same, right? So the determinant of E3 is just... except that the C just referred to the first elementary matrix. So this is just we've done this to the identity matrix. So what does it make it determinant? Just one. Good. Yep. So the determinant here is just one. And then just like before, if I do E3 times A, what is that? What does this multiplication, what effect does that have on A? Yeah, so it just, yeah, exactly. It just does the same elementary row operation, right? Does that change the determinant? No. So that's just determinant of A, which is 1 times the determinant of A, so it would still have determinant of E3, determinant of A. Okay, so far, we've shown that if one of my matrices is an elementary matrix, then the determinant just splits up over that product, right? Right? So let's see if we can continue with this. Well, what do we know about invertible matrices? If a matrix is invertible, how can we write that matrix in terms of elementary matrices? It's a product of them, right? Right? So let's do 2 cases. Let's say case 1, oops, B is invertible. Then B will be equal to, I should say A, let's do it this way. Sorry. Then A is E1, E2, out to En, where each E sub I is invertible. So what happens if I take the determinant of A times B, or any matrix B that I can multiply by A? What happens here? Well, what can I replace with A? Yeah, I can put the matrix in there. And what did we just show in the previous steps? If I have elementary matrix times another matrix, what can we do with the determinant? Distribute it across the product, right? So this will be equal to the determinant of E1, determinant of E2, determinant of En, determinant of B, right? We already said we could break it apart. Do we agree? Yeah? Okay. Well, now let's just concentrate on everything in front of the B. I can put that back together, can't I? Right, so this would be determinant of the product of E1 out to En. The reason why I can put it back together is because I can think of sticking in a determinant of I here. Right? Determinant of I is 1. So I can put a determinant of I in here and just put it back together with an I right here. And then, since the identity, it doesn't matter that it's in there. But what is E1 times all the way out to En equal to? A. Okay, so, whoops, wrong spot. So what did we just show here? We said that if A is invertible, what happened to the determinant function? It can distribute over any product that we have, right? I said that was case 1, so better have a case 2. So case 2 is where A is not invertible, or A is singular. Okay. If A is singular, what happens when we put A in reduced row echelon form? What has to happen when we put A in reduced row echelon form if it's singular? What has to be a characteristic of that reduced row echelon form? It has to have a row of zeros, right? So that means that there's a sequence of row operations where I get this down to some a product of elementary row operations times another matrix where the C has a row of zeros. Right? We know that if it's, think about it this way, we know that if it's invertible, its reduced row echelon form is the identity. So if it's not invertible, its reduced row echelon form has to have a row of zeros in it. Without a doubt, right? Okay. What do we know about matrices that have rows of zeros? Well, you do the cofactor expansion, right? If I expanded along that row, what would happen to the determinant?
0.
It'd be 0, right? So any matrix that has a row of zeros in it has to have a determinant of 0. Right? If we think about it from a volume perspective again, one of your dimensions is 0. If one of your dimensions is 0, it makes the volume 0. Right? So this tells me that the determinant of A would have to be this determinant of this mess. Oops, why did I write a 2 here? This should be an N. Has to be 0. And again, the reason for this is I could split, there's a couple of reasons why you could think about it. I could split the determinant up over the product. One of the pieces is 0, so the determinant is 0. Or if I take any matrix that has a row of zeros in it and multiply it by any other matrix, what's going to happen? I have to have that row of zeros in it again, right? All right, so if this is true, what's going to happen to AB? If I do the determinant of AB, it's going to have to be 0 as well, right? Because this determinant becomes E1, determinant of E2, determinant of En, determinant of C times B. That's just breaking it up like we talked about before. Right? But C has a row of zeros, so C times B also has a row of zeros. Right? So this part has a row of zeros, and what's the determinant of anything with a row of zeros in it? 0. So this will be these determinants times 0, which is 0, which I can also write as 0 times determinant of B, right? If it's 0, I can certainly write it as 0 times determinant of B. Yes? Which is determinant of A times determinant of B. So what did we just prove with all this mess? It was a lot of work. But what did we just prove happens with the determinant function? It distributes over products, right? So the theorem is, that was the whole reason why I went through all of this mess. Okay? The theorem is that for any n by n matrices A and B, the determinant of AB is determinant of A, determinant of B, no matter what the matrices are. I know it was long-winded, but we got there. This is the important part for determinant. We also got some things along the way, besides just this particular property. We got this along the way. If A is invertible, then determinant of A is not 0. We got this along the way because if A is invertible, how can we write it in terms of elementary matrices? It's just a product, right? Is it possible for an elementary matrix to have a determinant of 0? No. right? The only possibilities for elementary matrices determinants are 1, if it's the complicated row operation, right? Stay the same. -1, if you swap 2 rows. Or a non-zero constant, if you multiply a row by a non-zero constant. Right? Those are the only possibilities. If A is a product of elementary matrices, and the determinant splits up over those elementary matrices, you're taking a product of a bunch of things that aren't 0, which means it's not 0. Okay. We also proved that if A was singular, then its determinant was 0, right? So not only this, we actually proved the reverse. If the determinant of A is not 0, then A is invertible. Which means we really have an if and only if proof here, don't we? An if and only if statement, I mean. Right? If A is singular, we know it has a row of zeros in it. When we put it in reduced row echelon form, which means its determinant had to be 0. Right? So if it's not invertible, then its determinant is 0. So we've actually got the contrapositive here. We have if and only if, which means that being invertible is equivalent to determinant not 0. Remember your sheet of properties? You have another one to add to the list. So on that sheet, that extra sheet that I told you to keep track of, what are we on? G now? Yeah. You can write for property G, determinant of A is not equal to 0. So wherever you got that extra sheet, put that one on there. What's that, number 7 out of, I think, 21 by the time we're done with this semester? I'm pretty sure we get up to 21, so.
So we're putting like that if the determinant of A is not equal to 0.
Yep, that's literally the next property. It's just the determinant of A is not equal to 0. And you should be able to just write G, determinant of A is not equal to 0. Okay, just wanted to add. There's one more thing that we proved. If A is invertible, then the determinant of the inverse of A is 1 over the determinant of A. Now it's a little bit more buried, but it's in the property. What is A times A inverse equal to? Well, in terms of matrix, it's the identity matrix, right? Yeah. So A times A inverse is the identity matrix, right? So the determinant of A times A inverse is the determinant of I. What's the determinant of I? 1, right? So we have determinant of A times A inverse is equal to 1. Well, what can we do with that determinant function with respect to the product? We can break it up. So you get determinant of A times determinant of A inverse is 1. And then just divide by the determinant. Okay. So we also proved that. So that was, I mean, this is sorry, try that again. The determinant breaking up over products is an important property, which is why we went through that whole long-winded explanation of why it works. But along the way, we got other very important properties of the determinant. Okay? These two in particular are very important. All right.
We need to add that one to our sheet then.
No, this is just the property here. This is just another property for the determinants. Okay. So next time we'll play around with some of these properties of determinants to do some calculations. I've also got I have another video posted I would like you to watch for Friday. It goes along with the cofactor expansion and creating a new matrix called the adjoint matrix. And also this last property we just talked about here pops up. So it's about 10 minutes long, I think, that video. It's not very long. I'm trying to keep them to 10 minutes or shorter. I don't want it to be, like I said, I don't want it to be cumbersome. I just want stuff to have introduce things before you come to class.